This video is on volume by using the cross-section method and also the double integral method. So here I have the cylinder with the equation x squared plus y squared equal to 4, which is this cylinder right here. And I want to find the volume that is between the x, y plane and the plane z equal to x. Once again, this is the graph for x squared plus y squared equal to 4. So recorded to draw this the graph for this cylinder right here, and then on the xy plane here, draw the circle x squared plus y squared equal to 4. So on the x-axis here, this will be 2, and then on the y-axis, this will be 2. And then extend the circle here, extend it indefinitely on the z-axis, above the z-axis, and also below the z-axis. But what I want to do here is find the volume that is between the xy plane and the plane z equal to x. So this is the plane z equal to x right here. So the set of points that are on this plane will have the z and the x equal. And therefore the angle between this plane and the plane x, y, the two planes here, will be 45 degrees. And once again, I want to find the volume of this piece right here. So on the xy plane, this is region R. And so now what I'm going to do is find the volume of this solid right here by using the cross-section method, and then I'm going to use the double integral method. So the cross-sections, they would look like this. And notice that this solid right here is symmetric about the x-axis right here. So this is 2, this is -2, and this is 2. So we can find the volume from 0 to 2 on the y-axis here and then double it. So this is the cross-section at y equal to 0.5, and here's the cross-section at y equal to 1, and then here's the cross-section at y equal to 0.5. And so notice that the cross-section here, they just right triangles, and so the base here and the height, they're the same. The reason they're the same is because the plane, the angle between the plane z equal to x and the xy plane, they at 45 degrees. And so the base here and the height here, they are the same. So once again, the cylinder here is the equation x squared plus y squared equal to 4. And if we solve this equation right here for x in terms of y, then we get x to be the square root of 4 minus y squared. For this particular triangular cross section right here, y is 1.5. And so to find the x at this point right here, then in the place of y, we would have 1.5, and then be 4 minus 1.5 squared, and then take the square root, and that will give us the x at this point. And so in general, for a given y, then we can find the x with this equation right here. But the distance from the y-axis to this point right here, this is the base of this triangle. And so the base of the triangle is going to be the square root of 4 minus y squared. And because the angle between the xy plane and the plane z equal to x is 45 degrees, this angle is also 45 degrees. And therefore the base and the height of the triangle are the same. And so the height is also going to be the square root of 4 minus y squared. And the area for this triangular cross-section is going to be 1/2 the base times the height, or 1/2 times the square root of 4 minus y squared times the square root of 4 minus y squared, which is 1/2 times 4 minus y squared. To find the volume of the solid from y equal to 0 to y equal to 2, what we're going to do is divide the interval from y equal to 0 to y equal to 2 into n sub-intervals, like y sub 0, y sub 1, y sub 2, y sub 3, all the way up to y sub n, which is 2. And then let delta y sub I be the width of the ith sub-interval, and then for each sub-interval we're going to get a triangular cross-section with the thickness of y sub I minus y sub I minus 1. And so delta y sub I also represents the thickness of the ith triangular cross-section. And so the volume of the ith triangular cross-section is going to be a of y sub I and the times the thickness, which is delta y sub I. And then if we have an infinite number of cross-section of triangular cross-sections, then it's going to be written like this. And this is the area of the ith. This is the area of the ith cross-section, and this is the thickness of the ith cross-section. And just like before, when this limit here exists, then we defined it as the integral from y equal to 0 to y equal to 2. And then here we get 1/2, and then 4 minus y squared, and then dy. And then to evaluate this integral, the integral for 4 be 4y, and then y squared be y to the third over 3. And then here we have the 1/2. Evaluating from 0 to 2, we get a thirds. And so this is the volume for the part of the solid from 0, y equal to 0 to y equal to 2. And so the volume of the entire solid, which is from -2 to 2, then we just double the 8 thirds, and that will give us 16 thirds. And so volume for the solid here is 16 thirds. And now let's use the double integral method, and we will see that we'll get the same answer. And now let's use the double integral method to find the volume of this solid right here. And so once again, we saw moments ago, if we solve this equation here for x in terms of y, then we'll get x to be the square root of 4 minus y squared. And notice that the solid is symmetric about the x-axis right here. And so we can find the volume from 0 to 2, y equal to 0 to y equal to 2. And so let's use the method of double integral with f of xy dx dy. And so the y will have constant bounds from 0 to 2, y equal to 0 to y equal to 2. And then the x will have variable bounds between 0 and this graph, which is the graph of the square root of 4 minus y squared. And so the volume of from y equal to 0 to y equal to 2, and it's going to be the integral for the y is going to be 0 to 2, and then for the x it will be x equal to 0 to x equal to the square root of 4 minus y squared. And then f of xy, which is the height function. And so this solid here is bounded above by the plane z equal to x. And so f of xy will be just x. And then and now let's evaluate the inside integral here. And so we have the integral of x, it is x squared over 2. And then evaluate from x equal to 0 to x equal to the square root of 4 minus y squared. Then we get 1/2 times 4 minus y squared. And then now evaluate this double integral. The inside integral would be 1/2 times 4 minus y squared. And then and then to evaluate this integral right here, we get 8/3. And this is the volume of this part of the solid from y equal to 0 to y equal to 2. And so volume of the entire solid would be 2 times 8/3, which is 16/3. And as we saw earlier, when we used the cross-section method, we also got 16/3. And that's the end of the video.